Hello everybody, my name is Carmen Tuca and I came from Horia Hulubei National Institute for Physics and Nuclear Engineering, Bucharest, Romania, and I intend to present you comparative dose rate assessment for VVR-S nuclear research reactor hot cell decontamination. VVR-S reactor was used for research in physics, biophysics and radiochemistry, mainly for radioisotope production. Characteristics: 2 MW nominal thermal power, fuel low-enriched and high-enriched uranium isotope. Distillate water was used as coolant, moderator and reflector. Thermal energy produced was 9.59 gigawatt-day. The reactor was operated between 1957 and 1997 without any incident and was permanently shut down in 2002. From safety reasons, the reactor was decommissioned between 2010 and 2020. Here we have a reactor overview. Here we have 5 hot cells used for radioisotope production. Samples irradiated in reactor were processed in hot cells. In hot cell number 1, sources were extracted from capsules and then transferred for processing in hot cell number 2 and number 3. Radioisotopes were produced for medical applications, for gamma graphs and for furnaces. Here we have some pictures of the hot cell number 2 for solid sample processing, number 3 for liquid sample processing. During the decommissioning, the radioactive wastes were measured in hot cell number 4 and then transferred with a trolley in hot cell number 5 in order to be evacuated. Radioisotopes production generated significant contamination inside the hot cells. The floor were contaminated due to the accidental liquid or solid substance leakages. The inventory estimated before decommissioning was 14.9 curie. The main radioactive contaminants with a half-life longer than 1 year were cobalt, cesium, europium and silver. Hot cells decommissioning consisting in following steps: radioactive waste evacuation, hot cells decontamination, internal surfaces radiological characterization, and finally dismantling of the internal parts such as equipment and stainless steel lining. The radioactive waste inventory was significant at about 10.6 curie, 71% from the estimated ones. The main radionuclides were cobalt-60 and cesium-137. There were resulted 2.7 tons radioactive waste at about 88 containers. Before hot cells decontamination, we assessed the dose for the workers, considering a highest potential worker exposure inside the hot cell number 4. Due to the fact that the mechanical arms are broken and the process was performed manually. Dose was estimated by standard method for floor contamination scanning and decontamination and by numerical method for floor decontamination. The dosimetry worker could be potentially external exposed and the mechanical worker could be external and internally exposed. The dose rate for the workers is calculated based on the hotspot's radionuclide activity concentration, assuming that the sampling yield for the activity is 10% and the activity is concentrated in the hottest point. The total activity is equal with the sum of all hot points. Dosimetry worker perform ambient dose equivalent measurements to determine hotspots on the floor using a thermoscientific portable digital surveymeter placed at about 1 cm above the floor surface. Then he puts dosimeters with thermoluminescent detectors, tissue equivalent with high sensitivity for 1 hour in each hotspot in order to make parallel measurements. TLD's measurements were performed with reader analyzer TLD system, and the dose was calculated according to equation 1, taking in considering average reading of the irradiated detectors and dosimeter response to the photonic radiations. The ambiental dose results reveal that the mean value of the 6 hotspots is 50.7 millisieverts per hour, and in the case of floor scanning, and 28.7 millisieverts for TLD's measurements. The highest risk for dosimetry worker is due to A7 hotspot, and the values are 26 times and 27 times higher than the mean values. Then, around each hotspot, samples were assembled on 100 square centimeter surface in order to determine the concentration activity. The A7 activity is 3 orders of magnitude higher than the mean value of the other 6 hotspots. Thus, the ambiental dose rate measurements are confirmed. The external penetrant dose equivalent due to a single hotspot for dosimetry worker was calculated according with the equations, considering the measured activity of a sample and the sampling yield of 10%. Penetrant dose rate for dosimetry worker is presented in this table. The dose rate due to the contribution of the contaminated area is calculated according to equation 6. The total dose rate is 3.4 millisievert per hour. The risk is quite high considering a dose limit of 20 millisievert per year. After this process, the working time must be less than 5.9 hours per year. Floor decontamination was performed in 3 steps by the mechanical worker, 3 minutes each. Step 1 consisted in decontaminant spraying. Step 2 in hydrogel coating spreading. Step 3 in gel film removal. During the process, the worker could be potentially external and internal exposed. The total penetrant dose for mechanical worker is at about 8 millisievert per hour. The risk is very high considering the dose limit of 20 millisievert per year. After this process, the working time must be less than 2.5 hours per year. The internal committed effective dose for mechanical worker is obtained assuming that 10 power minus 4 of total floor activity is spread in air, and worker has mask filter 99% retention efficiency. The internal dose is low enough. The main contributor is A7. The internal irradiation does not affect the worker due to the high filter efficiency. The second method used for dose assessment is based on ResRad build computer code developed at US Argonne National Laboratory for doses and risk estimation from residual radioactive materials. A single ResRad build run can model a building with up to 3 compartments for source geometries, 10 distinct source locations, and 10 receptor locations. External radiation penetrating surfaces is calculated considering shielding, thickness, and density of materials. Internal exposure is calculated considering an air quality model based on air exchange. Direct exposure models are used according to source geometry. Pathways considering in ResRad build modeling are inhalation, ingestion, external exposure, and radon exposure. The external dose from a contaminated volume source is calculated according to this equation, considering the exposure duration, fraction of time spent indoors, fraction of time spent in compartment I, the average volume source concentration of radionuclide, dose conversion factor for infinite volume source, and the geometrical factors. The mechanical worker external exposure assessment was performed initially and after 7, 14, 21 and 28 days. based on the correspondent remnant activity concentration, considering hot cell number for one compartment, source geometry area, circle 2-meter radius, one distinct source location, hot cell center, and 3 receptor locations, as well as 3 decontamination cycles, 12 minutes each. The modeling considers following input parameters: the exposure duration, indoor fraction, receptor location, receptor inhalation rate, receptor indirect ingestion rate, source type, direct ingestion rate, air release fraction, and source erosion rate. At the initial moment, the highest external dose rate evaluated with resveratrol is for receptor 2, who spread the decontaminant gel on the floor at about 3 millisievert per hour. Those for receptor 1 and 3 are quite similar. After 7, 14, 21 and 28 days, the dose decreases according to the remnant activity. After 28 days, remains at about 1% from the initial value. By comparing total dose estimated with resveratrol with dose estimated by standard method, we can notice the resveratrol dose is lower than the standard method dose. Conclusions. Dose rates obtained by standard method are in good agreement with the direct measurements of the ambiental dose rate equivalent. Total dose rate at the initial moment, conservatively assessed with resveratrol code, is 32% lower than the standard method dose due to the model complexity. The methodology used for workers' dose assessment in hot cell decontamination process is the proper one and useful in the similar exposure situations. Thank you very much for your attention.